Good morning, Michael.
Good morning, Matt.
I see you got really into it. You're following along what we did last time when we talked about graphs, and you've started to write down the function that we looked at, sine of x to the n.
Right.
And now we're doing a more general setting of f of g of x. So let's see if we can set up a model graph situation and see what it looks like.
Great, let's bring up a graph. Here we go.
Wow, that's a beautiful graph. You know, I just think it illustrates the point. So, Michael, take us through this graph thing and see how we get from x to g of x to f of g of x. And you can see that we've helped things by rotating one of the graphs so you can see
Right.
exactly what's going on.
So when this function y is equal to g of x, it's our usual xy plot, right? So we've got an x-axis, we've got a y-axis, and we've got this nice little curve explaining the function. To explain f, well, we set up a second graph, but now we do it in a different coordinate system. Y is going to be the argument of f, and z will be the output of f. That's what we've got here. Y is equal to f of y. No, z is equal to f of y. Got that?
Yeah, I got that. Now,
Do you see the composition then?
f of g of x. So we're starting over here with g of x, and then we're using g of x as the input to f of x, f of g of x, which is z.
And
Now-
I like this idea where you mention input. So for instance, I could take an x value like 3, I would plug it into the g value and I get some number like it might be 4. And then I take that 4, carry it over here, plug it into f, and that gives me some other value. F of 4 might be 7.
Yeah, so you just have to look at the graph like this.
Exactly.
Well, okay, so I see in addition to the graphs and the dashed lines, you've got two little white bars there. So take us through that first for g and then for f of g of x.
Well, so remember that when we were working with derivatives, we approximate a function by a straight line. So that's what this little straight line is here. And so we say y is, this function here, y is some slope times x plus some constant. And here the slope, normally we would write the derivative here, but I can just call that m. And that's what we have in the equation here.
Okay, now then that is going to be the input over here to y, so we're carrying, it's because the two y-axes are aligned, so that value carries over, and so this is now the input side, and the output side is down here.
Right. Again, we have inputs and outputs, and we have this little equation here, this guy, which is saying this is my linear approximation. Z is equal to y times the slope n plus c. So I've got one linear function here, another linear function here. Then I have to combine them.
Oh, so wait, you've got a y here, and it's z is equal to ny plus c, which is our approximation locally here. We've got the approximation locally here, so why don't we take that linear approximation and substitute it in for y, so we combine the two linear approximations.
Exactly. So here's the y. And say, okay, I'm going to take this y value over here, mx plus b, and plug it in. And I've done that.
I see you've done that at the bottom.
So here's the n, that was the slope from this equation. Mx plus b, that's the y. And then there's some constant c.
And now if we combine, you can see that the coefficient of x is nm, which is the product of the slopes.
Right here.
So if I take a look at that, it's obvious now what our combined approximation is in this linear sense, the best one. It's just mn.
So what happens is you get a product of two slopes. So here, when we're taking derivatives, we'd get this first derivative, which is the slope, and then a second derivative of the other function.
And I
they're
see
just
you've
multiplied.
used a notation which is going to be what we're going to look at next time. But if we apply this to sine x to the n, proof left for students, you get exactly what we got before.
Should we write that down?
Sure,
So sine is the function f. What's the derivative of sine?
cosine.
Cosine. It's evaluated at g of x. This is g of x. And what's the derivative of this x to the n?
nx to the n minus 1. And that's what we got last time.
High five.